Check 1 2, check 1 2.
We might be able to show that. Just rushing really this thing about people. Well, I mean, it's finding, but, yes, all. Still thinking like or something. It's-
Pretty incredible and all that stuff.
Yeah.
I'm gonna go there.
Okay, good morning, everybody. Welcome to Friday. Last day. We have several things this morning, so I want to get started even as people start filtering in. Do we have? Yep, so here's our session, a plenary session this morning. We have two speakers, and I'll invite our student moderators up in just a second. After this morning's session, we'll have a break and we have one concurrent session. And so I encourage everyone to fully participate in that. But without any further ado, I will invite our student moderators up to introduce our first speaker.
Hi, my name is Jody McLennan. I'm a rising second year grad student at the University of Iowa. My advisor is Allison James, and I do research on the energy levels of pulsating aurora.
Hey everyone, I'm Ethan. I'm a grad student fourth year at UCLA, and I'm mostly known for working on the Elfin mission. And yeah, my advisor is Vasilis. And today I have the pleasure of introducing Dr. Chigo Ngwira to be our plenary speaker for magnetosphere-ionosphere coupling. He's a research associate at the Catholic University of America with a contract position at NASA Goddard. On top of that, he also holds a senior research scientist position at Orion Space Solutions, which is a very cool company that does end-to-end space solutions for our scientific field for making like CubeSats and small sats from the inception all the way to the science. Dr. Ngwira received his PhD in experimental space physics from Rhodes University in South Africa, where his thesis topic related to ionospheric responses to geomagnetic disturbances. Continuing on that theme to this day, Dr. Ngwira has various NASA and NSF grants to model, analyze, and predict geomagnetically induced currents. He obviously does great work as he serves as a guest editor on multiple special editions and journals, such as Frontier and Advances in Space Research, and has also received numerous awards, such as the AGU Science for Solutions Award. And if that wasn't enough, Dr. Ngwira also spends a lot of time doing outreach and community service, something that is also very important to me and should be for all of us as well. And he is on the Zambian National Space Science Program Technical Steering Committee, has also completed AGU grants to increase STEM participation in Zambia as well. So I'm excited to learn more about magnetosphere-ionosphere coupling. Let's give Dr. Chigo Ngwira a warm welcome. Thank you.
All right, thank you so much for that introduction. Okay, all right, thank you for the introduction. I'd also like to say thank you to the organizing committee for inviting me to give this talk today, the tutorial about magnetosphere-ionosphere coupling. Now, when I received the email, it says, would you like to come and give a talk about magnetosphere-ionosphere coupling? I stopped there and I was like, I'm not an expert of magnetosphere-ionosphere coupling. And then I read a little further and it said geomagnetically induced current. Well, I'm neither a geomagnetically induced current expert, but I love geomagnetically induced currents because that's most of what I do. It concerns geomagnetically induced current. And so I agreed to give this talk, but I'm sorry to the seasoned experts that this is not an expert talk about magnetosphere-ionosphere coupling, but instead it's just a talk about how magnetosphere-ionosphere coupling relates to geomagnetically induced current, because most of the driving comes from that coupling between the magnetosphere and the ionosphere. So that's what I'm going to attempt to talk about this morning. Before I go ahead, I just want to thank my a lot of people, collaborators that I've been working with throughout my journey, and the names are listed down there. So thanks to them and for giving me opportunities and also just collaborating with them and helping me throughout my research career. So let's see, it's not moving. So this is going to be more of the outline of my talk, just a brief introduction about space weather and then how it relates to geomagnetically induced current. We'll talk about the coupling in the magnetosphere, ionosphere, and then try to attempt to link these to geomagnetically induced currents. So at this point, I just want to thank NSF because my funding comes from an NSF grant that has enabled me to be here today. All right, so when we talk about space weather, usually this is kind of, if you look to the left, the top left, that's kind of the picture that we get because we're talking about how the sun and the influence of the sun on the earth. And this is because of either the different events or activity that come out from the sun, how they travel or how they impact the earth on the other side. Now, there's different phenomena which of course affect space weather on earth. And those are all kind of listed in that or shown in that picture. And those are all happening at very different time scales. And this makes space weather much more complicated than one would think it is. But then if we talk about geomagnetically induced current, then what we are really interested in most of the times is coronal mass ejections, because coronal mass ejections drive the largest geomagnetically induced current or the largest magnetic perturbation that we have experienced here on Earth. And so you can see here at the bottom left is a picture of a coronal mass ejection that happened in 2012, sometime in July. Now, with space weather, of course, there's two sides to it. One is the science side, and the other side is the impact side. And when we talk about the impact, then there's a numerous number of impacts that result from space weather. And you can see in here, there's a lot, but I'm not going to go into any of these, but just to highlight that geomagnetically induced current, which are shown in the bottom right corner of this figure, are what I'm going to be talking about. And they affect either power grids, or they can also affect these oil and gas pipelines. They can affect the rail system, the electrical rail system. And so if I move forward, so what then geomagnetically induced current? And so in simple terms, then what we're saying is if we have a magnetic field and this magnetic field is fluctuating, then the end result is that this magnetic field, if you couple it to a resistive ground, then it can produce an electric field. And it's the electric field then that drives these currents through like electrical power systems. And that's the biggest concern, is that these currents, the geomagnetically induced current, have a very low frequency compared to the power system. So that's the cause for the trouble that we experience on the power system, because GICs disrupt the normal functioning of the transformers. Okay? And so if we go down here, so GICs can be kind of split into two parts. There's the geophysical part, and then there's the engineering part. When we talk about the geophysical part, then this involves space weather and geology. And in space weather, then we're talking about the magnetosphere-ionosphere coupling, which then gives rise to these fluctuating magnetic fields. But then this coupled to the ground resistivity or the ground conductivity then produces that electric field, which we see here. Now, it's important to note that when we're doing this modeling or looking at geomagnetically induced current in terms of coupling with the ground, then you have to take note that the frequency components are very important when you do that, right? And then in the bottom here is the engineering aspect. When we have our electric field, then we can try and model what that electric field will produce in terms of the power industry or the power impact. And so here you can see electric field, and then the A and B parameters in this equation actually relate to parameters that concern the electrical power system. And this, if it say the electrical grid, then that provides information about the transformers at the substation you're looking at. It will give you the resistivity of the wires that are coming into that ground station, and it gives you a lot more information about the substation, which then you can use to calculate the GIC flows. And with that, then you can make an analysis in terms of what the impact will be to your system. It's important to note that when we talk about GICs, a lot of times, I know people in the community talk about the BTT, and that's because that's the space weather component, which results directly from the changes in the magnetosphere ionosphere. But when you're really looking at GICs and you want to take it all the way, then the electric field is the most important parameter that you want to look at, because there is also the ground resistivity, the ground conductivity that is involved. And we have seen there's a lot of studies that have shown that because of the difference in ground conductivity, you can produce very different GICs when you model. And so that ground conductivity is a very important parameter. And I think these days there is a lot of 3D conductivity models that have been pushed through, and those are making a lot of kind of improvement in terms of our modeling of geomagnetically induced current. You might be asking, what does GIC really look like? And here is just an attempt to show you what GICs look like. So in the bottom of this plot is an actual GIC that has been measured at a ground transformer station. So this is in the neutral of the transformer. And then the first two panels show the magnetic field perturbation rate of change. So the rate of change in the X component of the magnetic field that we measure on the ground, and then the rate of change in the Y component. So the X component is the north-south, and then the Y component is the east-west component. And when we talk about why GICs matter, then that's an example of a transformer that was damaged due to geomagnetically induced current. And that's why the power industry pays a lot of attention to this. And if you have ever taken time to look at GICs or the papers on GICs, then you will realize that actually what is in this plot, which is a maximum of around about 12 amps of GICs, is by far less than what has been measured in some of like the high latitude countries. Because this is an example of a GIC at a mid-latitude location in South Africa. And so this is very small. But there are others, and I think you see one, I'll show something that shows GICs at high latitude, which tends to be much larger than what we're seeing in this plot. Okay, and so GICs in terms of the transformer matter because of this half cycle saturation. GICs flowing through the transformer cause the transformer to operate outside of this design limit. And when it's severe, then what ends up happening is that you can have these transformers damaged. If you have a damaged transformer, the end result is that you might have a power blackout. I know yesterday in the GIC and ground magnetometer session, there was a talk about GICs in Sweden. And what you're seeing there is a picture of a blackout in Sweden during the Halloween storm of 2003. And then, of course, the most popular of GIC effects is the Hydro-Quebec failure in Canada, which happened in 1989. And this caused the whole blackout of the Quebec province in Canada. And so a lot of attention on GICs because of these impacts. And so there's been a lot of federal regulation that has come into place. And so right now, all the power industry players in North America are compelled to take some kind of action against geomagnetically induced current because it's a national threat, right? Just imagine if we had no power, then a lot of things that depend on that power get impacted. Okay, so now in kind of trying to relate GICs to the sun, so we're looking at from the sun to the mud, and this is kind of a picture that you would look at. So you have solar activity up here, and then propagation of this solar activity. Let's talk about CME. So this CME is propagating. It reaches the magnetosphere. There's this coupling between the solar wind and the magnetosphere. which causes changes in the magnetosphere ionosphere currents. And these reflect on the ground as changes in the magnetic field that we measure, right? And when we measure these magnetic field on the ground, of course, there's an internal and external component to the magnetic field. The external component being being driven by the solar wind, but then the internal component is because of the earth that we live in that generates its own current in the core, right? So there's these induction processes, and that's where the conductivity comes into place. And so the conductivity is an important component. So we have these telluric currents, of course, then drive GIC electric fields. And the electric field is the most important parameter when you look at the GIC flow on the power grid. And so that's the end result here. So what I'm going to try to attempt is to focus on the space weather aspect, which means I'm going to talk about the solar wind, the coupling to the magnetosphere, and the geomagnetic field changes. I'm not going to attempt to look at the ground conductivity producing the electric field and what happens on the power grid. Okay, so this is a picture probably that most of us are very familiar with. This gives you an illustration of the different current systems that exist in the magnetosphere. And of course, as you can see, there's a number of these current systems, and the whole system in general is a very complex system. And of course, if you treat the magnetosphere as a one-way system, you might actually miss out on a lot of components because there is a feedback mechanism to it. And so looking at it from a system science perspective probably gives you a better idea of what is happening in the magnetosphere. Now, if you are a modeler, then you want to make sure that you capture all these current systems in your modeling to be able to produce an accurate picture of the magnetic perturbations on the ground. And I know there's a lot of work in terms of modeling. I know the APL group is doing a lot of MHD modeling. The Michigan group and the UTA also doing a lot of this MHD modeling. And so unfortunately, in this talk, I don't include any modeling aspect. I just attempted to kind of stick to the data. And so most of what I show in here is all related to data components. All right, so looking at the magnetosphere ionosphere coupling, of course, Danji in 1961 then came up with this idea and suggested that this magnetic reconnection in the tail, probably there was something in the tail, and this in the tail connected to what we were seeing on the ground. And so there was this magnetic field from the sun, then interact with the earth, and there was some changes in the magnetic tail that were producing like the aurora that we see. And so since then, the community has gradually accepted Danji's theory of what magnetosphere ionosphere coupling is, and a lot of what we do today is based on that. Now, in terms of reconnection, of course, there's been a lot of theories about what reconnection involves, but I think one of the greatest achievement we've made is that since Themis mission, I think some of this has been resolved in terms of our understanding of what magnetic reconnection is. Right? And so, unfortunately, the magnetosphere ionosphere coupling is still a very big unresolved problem. There's still a lot that we don't know about the magnetosphere ionosphere coupling. And so it's a major challenge that continues to exist. And for the decadal survey, this has been one of the top priority problems that has been highlighted in the survey. Okay, so this is a picture that kind of relates to this magnetic reconnection. So if you're looking at this, then you're saying the sun is on the far left of this picture. And then you have the solar wind that then propagates from the sun and arrives at the earth, the L1 point. So there's reconnection taking place on the day side, which is right here. And of course, this mostly depends on the orientation of the magnetic field embedded in the solar wind. So the BZ component of the IMF is important in this case. Whether it's northward or southward then is an important question, because that's what kind of triggers whether there is an efficient coupling between the solar wind and the magnetosphere or not. And if the efficiency is high, which then means that you have a minus BZ or southward BZ, then you have reconnection take place at this point. The magnetic field of the Earth couples to the solar, the IMF, and then it's dragged backwards to the tail side. And then there is a second reconnection point then which happens on the tail side. And after this reconnection, the snapping of the magnetic field, part of it goes out to tailward, but then there's a component that drives back towards the Earth. And that's the component then which when there's this coupling here, the changes in the magnetic field in the plasma sheet then drives what we see in the auroral regions. For example, we see aurora substorm activity happening, and there's an enhancement in the substorm current wedge. And these all reflect on the ground in terms of what we measure on the magnetic fields. And that's why in the high latitudes, we see a lot of dynamics concerning the magnetic field's fluctuation. And so that's where kind of a lot of people have focused in terms of looking at how large GBDT is because of that coupling that goes directly into that, into the high latitudes. Okay, now, of course, looking at the coupling between the solar wind, the magnetosphere, then with saying there's a lot of parameters out there that people talk about in terms of the coupling. You have Akasofo, Borowiecki, and also you have the newer parameters that talk about the coupling. And then you can also talk about the geomagnetic indices. You have the KP, you have the DST, you have SYMH, which is the higher resolution of DST. And then you can look at the AE index, which is the auroral electrojet index, and then the SML index produced by Supermag, which also relates to kind of the substorm and high latitude activity. But then all these parameters, of course, some of them being at very different resolutions, when you look at GICs, probably don't make much sense. But for GICs, I think the most important parameters that I've mentioned before is the electric field. But closer to the electric field, we can look at the BDT, which most people use as a proxy for GICs, right? And so obviously, we need to kind of look at GICs from that perspective where things make sense, which is the electric field. And so some of the parameters that people may want to relate to, like if you talk about KP index, and having a KP index does not really, let's say KP9, does not really give you a true picture of what the GICs will be. Because even with the KP9, you may not have as much GICs as you think. But you may have a KP7, KP storm that produces much larger GICs only because what matters for GICs is truly the fluctuation in the magnetic field. So you have to be careful when you look at GICs and not just use any indices to try and kind of relate to the GICs. So a close-up thing you would do would be to an index that closely relates to the electric field, then would give you a true picture of what the GICs would look like. Yeah, so I was talking about how in the tail you have this reconnection, and then you have these field aligned currents that then flow into the high latitude. And this flow, like in the substorm currents, then you can produce these aurora. And we know, of course, a lot of us have seen aurora, have seen pictures of aurora, which is a result of all this space weather coupling. So the aurora plays a very big role in terms of GICs. Now, not just because of its influence on the high latitude region, but also because we know that the aurora can expand depending on how much energy you put into the magnetosphere. And that is very important component because when the aurora expands, then what you're saying is that these dynamic currents that exist within the aurora can suddenly appear at locations where you don't really expect them to be. An example is like the March 1989 storm, which was a very strong storm. And we ended up having aurora moving southward, which was over the USA, and it produced very, very strong currents over the continental US, where you don't normally expect to get those large currents. And of course, if you have followed the story of the 1989 storm, it was not just the large impact that most people talk about over Canada, but there was also actually a failure of some of the power systems here in the US, over in New York, because of the 1989 storm. And that obviously is not very much talked about when you read the literature, but it's a consequence of that GIC and the Aurora expansion. And so we're interested to know how this boundary is moving, what is driving this boundary. So predictions of this Aurora boundary are important in terms of knowing where it will be and what the impact might be in those locations where it will be. So there's been a recent study, James Weingart, I think I saw him somewhere in here. He did a study looking at how you can predict the Aurora boundary from magnetic field perturbations on the ground. And so he has used this spherical elementary current system method to look at how you can use the ground magnetic field perturbations, producing these pictures you're seeing in the bottom left, right, and then you can determine the boundary, which is shown here by these purple crosses in there. So you can see that on this day, which is the December 20, 2015, the Aurora moved southward, which is downwards to lower latitudes during this geomagnetic storm. See in this picture here, and you move to here, you can see it moving, extending down. And then in this picture, you see that there's been a significant expansion of the Aurora oval, which means then that you can have these dynamic currents that are usually at the high latitudes being seen in the northern parts of the United States. And this was not a very strong by any measure when you look at what the DST index was and what the other parameters like KP was for this geomagnetic storm. So it's a really, I would say, moderate storm. And we have had extreme storms, which would mean that you would see this Aurora expanding even beyond this point. And so what James has found out is that if you take the Z component and the velocity, when these increase, the SYMH index also increases. And you can see that in the midnight sector, there is a significant equatorial expansion of the Aurora oval. Okay. Now, what does the distribution of GICs look like on the ground? Where do we see the most GICs and where do we see the large GICs? So Pukenin did a study in 2012. And in this study, the right side represents the Halloween storm and the left side represents the March 1989 storm. And what you're seeing here is just the maximum of the electric fields at each ground station where there was a magnetometer. I think they used the intermagnet chain of magnetometers for this study. And so you have a global kind of picture when you take just the latitude wise, where you have from the southern hemisphere to the northern hemisphere. And then the zero here is at the geomagnetic equator. And you can see obviously from this that the largest electric field are produced right here in the Aurora oval section, right? So you have the high latitudes where you have the largest GICs occurring. And then in the middle panel here, strange enough, you see something kind of spike in the equatorial region. And I'll come back to that. And then in the mid latitudes, of course, where most of like continental USA is, it's kind of the point where you're seeing much lower GICs. I had promised that I would show you GICs at high latitude, and you can see here, I think this was from Finland. So this was GICs measured at some location in Finland. And you can see here in this here, GICs that reach almost like 60 amps in measurement. So this was a large GIC event that was measured. And this was during the Halloween storm event of 2003. All right, so we have this picture of where the most GICs occur. And then now the question of what is happening on the ground when we have this coupling between the magnetosphere and ionosphere? What are we really seeing in terms of the picture on the ground? And if you look at most of the geomagnetic storm, especially the extreme kind of storms, what you will notice is that you will not get this coherent picture where you have almost like very similar magnitudes in terms of the DBDTs or the electric field if you went that further to model. But instead, what we see is that during most of these storms, there's this picture where you get locations where there's these very large amplification of the DBDTs compared to other locations. And of course, the question is then what's driving those particular, I would say, structures that we are seeing in terms of DBDT. And so here's an example you see from this storm. This is the Halloween storm. You have in the North American section, you have this station around here where you have this very large DBDT or magnetic field perturbation rather. And then you compare to these other stations and you see that most of them have, it's not comparable to those stations. And so we're trying to ask ourselves, what is driving this localization on the ground? There's been some recent studies. Christine, one of those that were looking at these mesoscale features from the ionosphere, magnetosphere, and how they can impact things on the ground. And so there's an interest to understand these mesoscale and mesoscale features and how they relate to what we see on the ground. And some of this, I think there was a recent study. And one of the theories that is being proposed that it could be these wedgelets that we're seeing that might be producing that localization. And here, what I've shown here from this study by Otani and Jasper is this substorm or the field aligned currents rather. And what we're seeing is you have two pictures here. One is that this could be the picture that we truly have where you have just this one large current system flowing into the high latitudes. But then there's also a proposal that it actually could be these small wedgelet currents that are flowing individually into the high latitudes that are producing this kind of picture we're seeing here. And so there's need to obviously understand these and determine which picture is the right picture in terms of producing what we're seeing on the ground. And so there's future missions, of course, that are planned that might help us in terms of addressing this question, because what we have right now does not adequately cover in terms of data that we're getting to be able to answer this. A lot, especially if you look at the ground, there's a lot of sparsy magnetometer chains around, especially in the North American sector compared like to the European sector. So we need more magnetometers on the ground, and also we need to cover space. And so these missions are going to help us. And as the number of magnetometers increase on the ground, then we can cover from both sides, on the ground and on space, and try to answer these questions. Right. We did a study some time back trying to look at specifically this problem of these localized features that we're seeing on the ground. And here's an example from the March 9, 2012 storm, where we looked at what was happening in the North American sector, specifically over Alaska. And we had, if you look at the chain of stations in Alaska and you calculate the DBDT, you find at one location, this ground station, there was a very large amplification of DBDT compared to the other stations. And of course, this is the same question I asked, what is driving this? And so we were interested to see and answer this question. So on the right side, this is DBDT produced from the spherical elementary current system. And those of you that may not know, spherical elementary current system involves this method of interpolating magnetic fields at locations where you don't have a magnetometer. And so you use the stations, which are the green locations you're seeing in here, and be able to produce magnetic field perturbations at other locations where you don't have magnetometers. And so this gives you a picture now here of what the response of the DBDT was when you look at it from a 2D map. And you can see these two different time steps at 8:47 and then at 8:48, a very different picture in terms of what you're seeing on the ground. There is this very large enhancement over Alaska, which happens within that just 1 minute. And so this is the exact picture I was showing you of these localizations. So we explored this further by looking at the aurora images. And what we find is that during this time, we have this very large amplification. Lo and behold, there's substorm activity taking place right at that very same time. And what we found was actually that the substorm onset was close to the ground station that had that very large amplification. And as time went, there's this expansion of the aurora that then sweeps through the other station, and we can see it moving, and you can see the structure and the DBDT changing as this forward expansion of the aurora is taking place. And we know from other studies that the forward edge of the aurora drives very large currents. And this is the exact picture that we're seeing that's producing these large DBDTs on the ground. Then this is something very recent. There was a study, Angelopolis 2020. They looked at this magnetotail driving these large geomagnetic storms. And fortunately, on this day, there was Themis mission satellites 5, 3, and 4 were in the tail. And their location was such that they were directly in the line, very close to the plasma sheet, the middle of the plasma sheet, that they were able to see what was happening in the tail side. And then we can relate this directly to what's happening on the ground. And so they did capture this magnetic tail reconnection event. And so if you look in the middle picture here, you can see what was produced on the ground. Now, there's this very large DBDT compared to this. If you look at the stations that are within that circle, it's very large compared to the other stations. And then you have not so clearly seen, but there is these stars and crosses that depict the footprint of the Themis mission satellite. So they were very, very close in that point. And what we actually see is that at this very time that we see these very large DBDT changes, there was a very strong dipolarization event in the magnetic tail. And so this would presume drove these fastward flows into the high latitude that then produce what we're seeing here. And if you look in terms of the ground stations, then what we're seeing on the left side, you can see these images from the Aurora Oscar images. Unfortunately, the station, which is at Gillam here, was clouded on this day. But fortunately, you can get the intensity from that location. And what you can see here is, again, right at the time of this substorm onset is the time that we are seeing this strong structure of DBDT enhancement. And so we think this is related directly to what we're seeing on the ground here. So I go back to that picture I'd shown you of this global distribution of DBDT or electric field. And so here what we've done from the Pukanin study, which looked at 2 events, we went and looked at more events to try and see if this was a picture that was just maybe particular to these 2 extreme storms, or it was actually a picture that we see for many other storms. And so we looked at 12 different storms that were perceived to be extreme. And extreme, I mean, these are storms that produced a DST of at least -200 and below. So 200, 300, -300 and up there. And this is the same picture that you saw in that study that was done by Pukanin. And you can see here at the equatorial region, that enhancement still is there. And so then what is driving this low latitude enhancement at the equatorial region? And what we found from this study was that most of the times this was related to this sudden commencement And this drove very strong current enhancement in the day side. And this was producing this like penetration electric field that was penetrating right to the equator and amplifying the equatorial electrojet current. And so that's the driver of this. And then there was another study that was done later on by Brett Carter, and it actually shows the same thing that we found was confirmed by this study, that actually it was these sudden storm commencements that were driving this very large amplification of the equatorial electrojets. Well, let's not forget the mid-latitudes. We live in the mid-latitudes. So this is an ongoing kind of study. And what this study is showing is that you have these mid-latitude magnetic bays. And these mid-latitude magnetic bays relate to how the substorm current enhancement is propagated through to the mid-latitude. And you see it as this enhancement of the magnetic field perturbations at the mid-latitude. If you want to know more about these mid-latitude bays, I would suggest you talk to Bob McFarren, and he's done a lot of these studies. But what we show here is specifically that these mid-latitude bay are a potential source of large DPDTs. And what I'm showing here, you can see, now this is GICs that have been measured in the USA at some transformer location. That's what you see in the bottom here. And you can see very large large GICs, close to about 30 amps in this case. And you can see the BDT here. So I'm sorry. You can see very strong correlation, the BDT and the GICs. And then you look at the SYMS index, which is the high resolution DST. You can see there's this change in the magnetic field right at this time, which then shows this jump in magnetic field. And there was some enhancement in the density, just like about 10 minutes before this. And we think that this is actually the driver for the substorm that subsequently happened later on that drove these strong DBDT changes. And what you see on the right side is ground stations in the USA. And these are the different geomagnetic observatories run by USGS. And there's also Ottawa from Canada. But you can see in this blue interval is when you have these changes in the solar wind, this strong density enhancement there. But the brown area here, you can see the changes in the magnetic field. Simultaneously, all the ground station observe this jump in magnetic field. And that's what we're calling the mid-latitude positive bay. And you can see that this is the point which relates to this GIC over here. And so we have the evidence that these magnetic perturbations, mid-latitude bay, can actually drive very strong GICs on the ground. Another possible driver of GICs in the mid-latitude is these geomagnetic field pulsations. And there was a study recently that showed from the data in the USA, I believe this is a ground station somewhere around the US, you can see this GIC data, and they relate it to the geomagnetic field changes. You have SYMH index, and you can see how the correlation in those selected areas shows that there is very strong correlation between the GIC changes and the geomagnetic field changes, which are indicate here that there is some form of pulsations taking place round about that very time. And so I think this is still something that is kind of an open area for people to further investigate how these pulsations are related to the strong GICs. And so I'll end here in terms of looking at what the magnetosphere-ionosphere coupling and how it relates to what we see in terms of the DBDT changes or the GICs on the ground. And I'll just let you read through. I don't want to bore you by reading through that, but I think some of the important pictures or things to mention here is that this magnetosphere-ionosphere coupling is a very important topic when you look at GICs, because the drivers that pertain to GICs relate to this magnetosphere ionosphere coupling, which involves the space weather itself. So thank you very much. Before you bombard me with questions, this is a shameless plug. I am one of the organizers for this African Geophysical Society meeting that is taking place in Lusaka, Zambia, October 2nd to October 4th. Unfortunately, we have some funding from NASA and we're expecting some funding from NSF to be able to sponsor graduate students, postdocs, and early career scientists. And if you are interested to go and give a talk at this meeting, you can follow that website, submit an abstract. The deadline for the abstract submission is June 30th. Thank you very much.
Chigo, I really enjoyed your talk, and then so here I also learned the DST is very good and overall magnetic storm index, but not even nearly close to for the DBDT. And the same age, 1 minute, better still not. But so that shows your DBDT has a very local, regional associated with the GIC. But one thing I want to hope you can comment more is the GIC and then the influence to the power line has something to do with the ground conductivities, particularly their uniformly conductive or different conductivities. That will have some impact, actual impact on the power line, the transformers.
Yes.
Yeah. Can you comment on that one? Maybe explain more to.
Yes. So depending on where you are, the ground conductivity can be very different. And then you have these lateral changes in conductivity where if you look at two different contrasting cases, let's say I pick a 1D case where I'm just saying the ground conductivity is uniform, or I pick a case where I take the lateral variation in the conductivity into place, then the picture will be very different in terms of the GICs that are produced by these two different conductivity models. And that is exactly the case that has been shown. I know Jeffrey Love has produced some results which show the difference between a 1D conductivity model and the latest, greatest, these 3D magnetic tensors that have been produced by the USG, this USRA project. And it shows that we need to take into consideration the full 3D picture of the ground conductivity to get a true sense of what the electric field is on the ground. And so it's important to consider that.
Thank you. Yeah, I have one comment and one request. And the comment is that in one of your slides, you emphasize the importance of dayside magnetic disturbance right after the arrival of shock. And in my view, that's likely cause of the Colaba magnetic depression during the Carrington storm. So I like to emphasize that it's not just the main phase, but it could happen, large DBDT could happen right after the arrival of interplanetary shock. And the one request to you, not necessarily only to you, but to the community, is that I'm a member of SuperMag, and SuperMag has been supported by NSF based on data set provided by an international institute. And for the next operation phase, we are thinking about new indices or new index or indices associated with DBDT. And so if you have any idea what would be most interesting in the GIC community, we would be glad to implement. And so any comment or suggestions, it's very welcome to Jasper Gujrov, PI of SuperMag, or myself, Shin Otani, or SuperMag. If you go to SuperMag website, you can input your idea to the team member. So those comments are very welcome, especially because GIC is getting more and more attention, from the community. So I enjoyed your talk very much, and I appreciate your thought.
Okay. Thank you very much. And maybe just to comment a little bit about what you say concerning the Colaba issue. And I know this is kind of a big debate on itself as to what exactly drove this large not GIC, but magnetic field perturbation at Colaba. And I know you have a paper on that, and there's been some papers that respond to what you say. And so I think the debate is still going on, and there's still a lot that we don't know in terms of the GIC drivers, and that relates to the magnetosphere ionosphere coupling. And so there's so many questions that we still need to answer, and the Colaba issue is one of those activities that still needs to be kind of looked at and determine exactly what drove those large currents at that very low latitude location. What I had shown in here are just specific cases that we look at that were caused by sudden storm commencement, and not necessarily that all the large currents that will be produced at those low latitude regions will be from sudden commencement. No, some of them might not relate to this sudden storm commencement. Thank you.
Sorry, let me go real quick. We have a question online from Charles Chappelle. I'm just going to read it out. What do you think about the ionospheric outflow from the polar cap out through the lobes of the tail into the plasma sheet region and its result on the plasma sheet merging location and strength? And Charles, if you want to chime in, feel free to unmute.
Can you read that again?
Sure. What do you think about the ionospheric outflow from the polar cap out through the lobes of the tail and into the plasma sheet region and its results on the plasma sheet merging location and strength?
Well, as I said earlier on, I'm not a magnetosphere ionosphere expert. And so when you talk about what is happening in the tail side of the magnetosphere, I'm not completely sure of that. But I would say that probably if there's an impact of this, what that happens in the tail, that is then transmitted to the high latitude, probably it might produce some magnetic field perturbations, which we probably maybe just don't understand right now. And there might be a connection or there might not be a connection. But I guess that is still something that is still open, and we can probably further investigate this.
This is Rick Chappell. If I might add to the question, is that okay? Should I go ahead and comment?
Sure.
We know that the polar wind and the polar cusp supply upward outflow from the ionosphere constantly. That moves out through the lobes. When the solar wind BZ changes at the nose of the magnetosphere, that changes the crosstail potential, and all of this plasma that flows out of the ionosphere, which is very cold, is pushed into the plasma sheet. When that happens, it changes the entire merging conditions in the plasma sheet, because the density and the energy of the plasma there goes up and the merging can be enhanced, both in its strength and in its location. It can move closer to the Earth and hence farther to lower latitudes in the ionosphere below and affect your GIC's location. I just wondered if any of the data that you've looked at includes the measurement of the outflowing cold ions through the lobes, which then affect the merging that goes on in the tail.
Well, there you have it from an expert. Thank you very much for the question. You've just let me learn something new today. Yunju?
Yes, thank you for the very nice talk, Chigo. I do have a question. So I've been seeing that there is some clear, different atmosphere. Like we are excited to learn about the GICs, but power company don't care, right? So you show the pulsation results. Can you go back to that slides? And you show that the PC5 pulsation related with the GIC pulsation there. And then I'm looking at the magnitude, it's about plus minus 5 ampere. Do they care? Should we focus on that? I don't want it to focus on something they don't care. So
Well, so this is a very kind of say relatively new study that kind of shows that there could be this relationship. As to how much really these pulsations will drive in terms of the GIC amplitude is something that probably needs further investigation. But in terms of the power community caring, I would say that I think right now, as things are moving, obviously, all the power industry people do care about GICs because it's a federal regulation that they have to take GICs into some consideration. And so they do care. But I think if you just spoke like maybe one-to-one with the power industry person and you show them 0.5 amps, they'll probably tell you, I don't care, right? Because it's very small and they wouldn't care about that much GICs as it pertains to what the impact would be on the system. But if, for instance, maybe the pulsations were able to drive much larger GICs, then I would say that they would care probably about that pulsation.
Yes, so then how large is to them so that we could focus on that? Because if plus minus 5 is not really large GIC to them, then I don't want to focus on there. I want to focus on something, the larger events that cause larger than plus minus 5. Would you give us some guidelines so that we don't spend too much time on little thing and then focus on really important matters?
Well, according to the federal guidelines, I think they are compelled to take some kind of action if they see something. I think it's about 50 amps or so. I might be wrong.
50
Steve, do you
amp?
know the number? Is that 50 amps correct, right? It's something about 50 amps or more. It was 75. Yeah. So around that much, if they see that much, then they're compelled to take some action, right? But you should also understand that right now we are in, the last solar cycle and this solar cycle has not produced that many big events that would impact GICs that much. And so it's not just about them caring on having this number, but it might be that we might get a storm that might drive all these much larger currents. Because we have seen much larger currents than even 50, 80 amps. There's been places where 100 has been measured, 120, 150. So there is some potential that you could have storms that will produce very large GICs. And I think if you don't need to throw away the smaller storms which produce like 20 amps GICs, because we can still understand something from them in terms of the driving of GICs.
Thank you.
Okay, thank you. All right. Thank you, Chigo.
All right, thank you very much.
Okay. So I invite our next two student moderators up to introduce the next speaker, please.
Hi, I'm Espen Frederick. I'm currently will be a third-year grad student this year at the University of Texas at Arlington. I work with Ramon Lopez, and we work on quantifying the unreliability of solar wind propagated from the L1 point and its impacts on models used for forecasting. And I'll be fielding your questions today. Hello, good people. I'm Hector Salinas, and I'm also from the University of Texas at Arlington. I work with Dr. Frederick Wilder on using MMS observations to analyze electric current structures and wave activity in the magnetosheath. And I will be introducing Dr. Steve Morley. Now, it was at the University of Southampton in the UK where Steve acquired his undergraduate degree in astrophysics, but with a solar physics-focused final project. That research shift will translate into Steve being awarded his PhD in 2004 at the same university, where he studied ionospheric responses to transient day-side reconnection. Following those university days, he would go on to do a short contract with the British Antarctic Survey and postdoc at the University of Newcastle in Australia, which involved studying magnetospheric substorms and working on magnetometer operations for the Australian microsatellite mission known as FEDSAT. Since 2009, Steve's been attending these here GEM workshops and been a part of the Los Alamos National Lab Space Science and Applications Group, where he's currently a senior staff scientist. His current research include ensemble modeling methods, modeling space weather impacts on satellites and power infrastructure, statistical modeling, and data model fusion, and other things. When he's not doing research, he's tending to his infant son. Now, give it up for Steve Morley, good people.
I think that's the most exciting introduction I've ever had. So thank you for that. And that was probably the highlight. So if you are feeling like you're done, feel free to leave. Okay, I'm going to start a timer here so that I keep roughly to time because I have way too many slides. Thanks again for the introduction and to the student moderators, to the organizers, and most of all to everybody who's still being here on Friday. So the talk that I was asked to give was for the modeling methods and validation group. And I found it very, very hard to try to put a topic together for this. I wrote a whole talk and then threw it away because I didn't like it, which left me very little time to write this one. So hopefully this one works. I'm going to be looking at a couple of examples to kind of illustrate the concepts here. And so I'm going to look at a kind of a classic textbook example of tornado predictions. And I'm also going to follow on from Chigo's excellent talk, looking at GMD prediction. And GMD is geomagnetic disturbances, and that's kind of how it's referred to broadly by the power industry. It's just GMD. That's what they understand. And I think I like it as a term because it's a good catch-all. So, and what was the magic for the slides? Oh, here we go. Figured it out. So I wanted to start off by saying, well, you know, what is model validation and where do we need it? And my answer is everywhere. Because what is a model? Like if I say, well, you know, we're doing modeling, you might think of something like RAM-SEB. It's a drift kinetic ring current code that has a coupled self-consistent magnetic field model. That's definitely a model. I think we can all agree about that. If we want to predict things with it, we probably want to validate it. You know, there's DREAM, which is a data assimilative radiation belt model. It's a diffusion model at its heart. In the bottom left here, we have the SHELLS model, which is a machine learned model to predict equatorial electron fluxes from low Earth orbit data. And you know, it's a fairly complex regression model, but it's still a regression model. And so this is an empirical model. And the last model that I want to show here is the combined X-ray dosimeter that flies on the GPS constellation. You might be thinking, hang on, Steve, this is an instrument. Well, if we're doing model validation, models implement ideas or maths, and then you predict quantities of interest. And so we have this chain here. You know, I forgot to add profit at the end, but we go through and we try to predict something. And what ultimately is an instrument doing? Well, because you probably don't trust me, but you do trust the internet, I asked ChatGPT. There is a whole conversation that I had about this talk with ChatGPT, available at that QR code. Feel free to keep your phones out. There'll be a couple more QR codes. But with some prompting, because ChatGPT is not very smart, it said that particle detectors rely on models to convert your raw measurements, so your counting, into scientific quantities. And, you know, it very cleverly identified that things like detector response, background, et cetera, have to be taken into account. And so that's a model. And so when you are getting your flux out of your particle detector, that is a model output. And so you need to do validation, as it says here, against independent experimental data. So regardless of what you work on, whether you think you're a modeler or not, there are models involved in your work, and model validation is important. That's my pitch. Okay, so a little explain, like on 5, I had on my previous slide, it was one of my steps, verification, validation, and accreditation. And it's a huge formal area of study. It's mostly used for big engineering projects, government projects, that kind of thing. And it essentially is posing 3 questions. Did I build the thing right? Did I build the right thing? Subtly different, but very importantly different. And the accreditation part is it believable enough to be used? So the figure here shows the research lifecycle from the application usability level framework. And the reason I like this is because it demonstrates the forks in your research path. As you've moved through this phase with testing and validation, you can fork right back to earlier in that process. Because if you update your model configuration or user requirements, you may need to redo your validation to address those. So what's the difference between these two very similar questions? Verification is basically saying, does my code correctly compute what it's intended to? So that might be, your testing that your model converges as you change the grid, for example, as you increase your resolution. It could be as simple as, I have a function here to integrate something. Does it actually integrate properly? And the great thing is you don't need data for that. You don't need any data at all. You can make everything up, nice contrived examples, test, test, test. And we should absolutely be doing that. That's all I'm going to say about it, though. Validation is, did I build the right thing? And it doesn't matter if you're integrating correctly if you're not representing reality. And so validation is saying, are we representing reality to the degree we need to for our intended application? And that's done by comparison with data. Okay, so for most of what people in this room are doing, you won't ever need formal BV&A. The concepts, I think, are still very important. I've got a little bit of terminology here. I am going to be talking a lot about metrics. And by metrics, I don't mean like, oh, well, I'm looking at satellite surface charging. Let's look at the integral electron flux. That's not a metric. That is a predicand. That is the thing you are trying to predict. So, or a quantity of interest. And so by metric, what I mean is a measurement, a quantitative number that describes an aspect of model performance. And aspects of model performance I'll hit in a second. But so, for example, the root mean square error, we all know that. That is a metric, and it's specifically a metric for accuracy. Okay. So validation is comparing model to data. Most of us have done that. How hard is this, right? Well, when we're comparing data, we want to describe how the model performs, but what aspect of performance are we trying to describe? There's a few different taxonomies for this. I like this taxonomy, which comes from the weather literature, Murphy 1993, great reference for this. There are other taxonomies, but they usually have a lot of overlap. And so what the metrics do is assign a quantitative number to one or more of these aspects of performance. So these are probably the better known ones in the room. Accuracy, which is kind of, actually, I'll get to that, but yeah, so these are the better known ones, and they're easy to apply to a wide range of data, whether you're looking at kind of a continuous data, like a time series, or a categorical prediction, like a yes/no event type thing. A little less well known, at least by these names in our field, would be this middle block. And they're generally assessed for either categorical predictions, so event predictions, or probabilistic models. And so if you were at Shine, like all of the FLAIR people would be like, oh, we know these because we do probabilistic FLAIR forecasting. Great. And so just as an example of the differences between some of these, accuracy is where you essentially, so y minus x in there, that is your error at any given point, okay? And so the accuracy and the error are different because the accuracy is aggregated. It's your is aggregated over the errors, and it tells you the average correspondence between your forecasts and observations. And it's not signed. It doesn't care which direction you missed. And that's one of the keys for accuracy, is like, what's the typical amount that you miss by? If you move to skill, often skill and accuracy can be used interchangeably in a conversational way. But if you look at this type of taxonomy, they're actually quite different. It's still related to accuracy, but it's accuracy relative to a baseline model. And so, to get to a skill, you have to understand, well, what is my baseline model? What's an appropriate one for this case? You also have to choose an accuracy metric in order to do that comparison. How much did the accuracy improve by for a given metric against a given model? And so there's prediction efficiency is in the field, like a name that we usually give to a very specific formulation of that skill score, where we're using a mean squared error as the accuracy metric and a sample climatology reference model. And so you know, there's a lot of little details to pay attention to, and all of this affects the meaning of each metric. And that's kind of what I'm hoping to get you today, is just like conveying the importance that I see in understanding what each metric is trying to tell you and how we can learn from doing this validation process. So I don't think we need this slide, so I'm not going to spend time here, but I'm going to be breaking things down into two broad categories. The figures here are from Mike Lamone's paper, RMSE is Not Enough, which is a great title. I wish I'd thought of it first. And he broke things down into, he was calling them fit performance metrics, which are for regression type problems or continuous data, and event detection metrics, which are essentially for categorical predictends. And so that's your classification problems. So if you're doing classification problems, and I'm going to spend most of the time on this because this is how it's done in a lot of the GMD validation. You're looking at contingency tables because they're a great way to summarize categorical predictions. So a contingency table looks like this. You have, you know, columns for your observed yes, no, or you can do this multi-category. And you have rows for the forecast, yes, no. There you can basically put a number in each box and then calculate a whole swag of metrics from here. And these are actually, you know, quite rigorous in their statistical underpinnings. And it's really fascinating to kind of dig into it. For example, you know, you can easily represent everything you can calculate from here as a probability. So, you know, the joint probability of a forecast event occurring at the same time as an observed event is just the number in that first box, the hits, divided by the total number of events. And that's pretty cool. You know, you can get conditional probabilities out of this. And so the example here is if you take that first box again, you divide it by the sum of that row, that's the conditional probability of an observed event, given that you forecast an event. And this gives you a whole different interpretation on what those numbers mean. The numbers haven't changed, your scores haven't changed, but maybe phrasing it in this way changes how you read that number. So there's a lot of metrics and they have a lot of different names. And it's worth kind of paying attention to this because really what we're trying to do here is both communicate and understand. And, you know, words matter. So I mostly refer to the weather literature for this. You know, our space weather forecast centers, for example, mostly sit with weather forecast centers. And so there's a lot of overlap there. That's where I go for this community. And it goes back a really long way, which I'll hit soon. But for example, if you look at weather literature and you see something about the hit rate, that's the same as if you're reading a paper doing machine learning and they're talking about recall. Those are the same thing. There's no difference. It's also, if you're more statistical in nature, the probability of detection. And that's a measure of discrimination. So whether you can tell events apart. There's another one, false alarm rate, not to be confused with the false alarm ratio, which is a totally different thing. And that's your type 1 error rate if you're into your stats. Okay. Accuracy, the proportion correct is a very simple accuracy measure. And in machine learning, they're very straightforward. They call it accuracy. There are other measures for accuracy, though, because in this taxonomy, you have accuracy is a type of model performance that you can describe in different ways. And so, you know, things like the odds ratio may be useful for describing that accuracy. There's skills, there are associations, there's every category I listed has measures here. I also note that there are differences in how the tables themselves are called. Like I said, they were contingency tables. You pick up any stats book, you'll see contingency tables. In machine learning papers, they're generally called confusion matrices. And watch out because they will confuse you by switching the order of the columns, the rows, transposing them. And so just, you know, read the labels, don't just look at the table. And the most confusing thing is the fact that model validation in every field except the one that has done the most work on it is called validation. And in weather literature, they call it forecast verification. And so I wanted to use this as a quick example for why they do that, but also then lead into okay, what do some of these metrics actually mean, and why are they important to look at in multiple ways? So this gentleman with the very nice coat and the fantastically flamboyant mustache is John Finley, and he worked for the US Army predicting tornadoes for the Western US. He wrote up his results in a paper in 1884, which is, I don't know, probably when I was in grad school. And he did performance assessment of his tornado forecast. It's a very early example of this formal validation work. But, he was a US Army engineer. It was new in the field. He called it verification of predictions, which is totally understandable. And it's stuck in weather literature, and nowhere else really cared or knew he existed. And so they came up with this VBNA framework, which has spread across most disciplines. So as our little example here, I wanted to look at, was Finley's forecast any good? And so I've pulled up a set of common machine learning metrics here. I've put his numbers into this contingency table. He correctly predicted 28 tornadoes. He correctly predicted that nearly 2,700 would not occur. He had some misses, some false positives. And, precision and recall, even their alternate names, don't necessarily give me an immediate feeling for what is there. I mean, is 0.55 recall good? It feels good. Accuracy, though, that's something that I at least immediately see that and I go, I think I know what this means. And if you call it proportion correct, you probably even have a stronger feeling for that. 0.97, 97% correct. That's fantastic. And I live in a place that doesn't usually have tornadoes because I don't like tornadoes. And so my question would be, well, if tornadoes are rare, and I just say, well, look, tornadoes never happen. So that's going to be my prediction. Tornadoes just never happen. How right would I be? So that's called the majority class fraction, where you just predict the most likely outcome all the time. It's what they call an unskilled forecast. And you'd be right 98% of the time. So was Finley's forecast actually good? So we can look at this in a couple of different ways. And usually you see sets of at least 3 metrics to look at these tables, because that's what you need to fully encapsulate the information in those tables. So the first one here is the BHF triplet. So this is bias, hit rate, false alarm rate. And I've just called a couple of these out for how you might interpret them. So the hit rate or the recall is 55% of observed tornadoes were predicted. Now that I have a description of this, it makes a little more sense, and it feels better to me. The false alarm rate looks very low, and 2.6 of no tornado observations were incorrectly forecast. That's the simplest statement that I could make for interpreting the false alarm rate, and I'm still having trouble parsing it. It's like, is that good? Maybe it works for you. It doesn't work for me. If we go down to a different triplet that captures the same information, but just summarized in 3 different metrics, well, 2 different metrics, one the same. You have the odds ratio. Now, I'm sure that we're all immune to the vices of gambling, but the odds ratio tells you the odds were roughly 45-1 that a forecast for a tornado would be a hit instead of a false alarm. And that speaks to me. And maybe the false alarm rate interpretation speaks to you. We need to communicate these things in different ways because they tell us slightly different things in different ways. And then the frequency bias, you'll notice it's in both of them because it's actually a really good way of capturing some critical information, which is, am I over or under forecasting my event? And this tells us that almost twice as many tornadoes were forecast than actually occurred. And if you're in an operational setting, then maybe you care about the cost of a false alarm. And so this is critical information. So the point, hopefully, is getting across that, you know, interpreting a forecast or a prediction doesn't have to be a forecast. Anything your model outputs is a prediction, even your data. And so this requires multiple metrics. And there are a lot of them out there that all tell you slightly different things. So it's worth kind of thinking about not just what you need, but what somebody who uses your work might want to see. So here's the QR code for Mike's RMSE is not enough paper. And, you know, he has a good discussion in there where he says, you know, it's highly advantageous to use a robust suite of metrics. So hopefully I've kind of made that point. So I will spend the rest of my time talking about GMDs, something a little more relevant to this room than tornadoes, unless you live in Kansas or something. And then the thing I'm going to focus on is the search for the operational geospace model. So from kind of early days through to after the model was selected. So we have some points on the left-hand side of this slide from a report. I think it was a Department of Energy report about the steps required for formal verification, validation, and accreditation. And I wanted to show that actually, you know, there is a space physics example for this, which is the hunt for the operational geospace model. The outcome I'm going to ruin, the space weather modeling framework was transitioned to operations. When you go to the SWPC website, you'll see the operational geospace model, which is a specific configuration that was selected during this process. Couple of the important points, you know, validation needs to include a bunch of different people, formal validation, and that's the modelers, data specialists, the people doing the validation. And in this formal process, these are all different groups of people. And that was done in this process for looking at geomagnetic disturbance predictions with these models. The plan was defined in advance. That's another important step. You have to kind of define your experiment before you do it. And then the CCMC led those independent model runs. There was test data. Some of the events were known in advance. There were a couple of surprise events to hedge against anyone who was tempted to tune their model. Okay, and so, you know, there are some key things here which were followed in this case, and I think it's a really interesting case. So I'm going to work through this very quickly. And where I want to start is this paper by Antti Pulkkinen in 2010, where he was looking at ground magnetic field predictions from global MHD models, preparatory work for a GEM challenge. And here's just a couple of images from his paper, you know, looking at in the top left, the observed horizontal magnetic field vectors at a given time, and then results from 3 different models. And if you eyeball those, you probably say, this doesn't look great to me. And, you know, I mean, the clue is in the title. Early work was not tremendously encouraging. So what they're comparing, I'm going to put this in terms of what I was talking about earlier. Their quantity of interest was the horizontal magnetic field, and they were looking at this in terms of time series and power spectra. And so these are continuous or regression problems, okay? The metrics that they used for assessment, more than one, but still only 2, you know. And so there was prediction efficiency for measuring skill. And, you know, this is relative to sample climatology, as I mentioned earlier. And there was the log spectral distance, which is a metric designed to assess the accuracy of a predicted power spectrum. And so that essentially is giving you the overall distance between your predicted and observed power spectrum. The big takeaway from this was that actually all of the mean prediction efficiencies were negative, and negative prediction efficiency is negative skill. Negative skill, as you might imagine, is not good. Negative skill means you're doing worse than your reference model, which was the sample climatology. So if you literally predict the average, you do better than the model. However, while that sounds bad, this is kind of like the accuracy in the Finley example. If we look at something else that's perhaps a little more relevant, you know, Chigo mentioned that, the geoelectric field is what drives the impact on the power grid. The geoelectric field is essentially a filtered version of the geomagnetic field, because the solid earth acts as a frequency dependent filter on your magnetic field time series. And so the power spectrum, as you might imagine, is a good way to capture all of that frequency content rather than just looking point by point. And the model power spectra were actually quite similar to observations. Power at high frequencies could be underestimated by the models, and that was more common. Although that could, I think, in large part have been the specific model configurations being used. But the power spectra are good, and so that actually does show possible utility. And so that's great. It's a good reason to move forward, even if you can't predict the time series very well. So the next step here is the 2008-2009 GEM challenge. And so, this is right at the start of my GEM career, because I was, elsewhere before that. And so I think this is kind of a landmark paper, at least for the GMD type community. And so, again, looking at horizontal geomagnetic field perturbations, the time derivative was added this time. Chigo talked about a lot of the rationale for using the time derivative. And the time derivative essentially gives you a kind of a rough filter on the time series anyway. So, if we look at the two figures here showing kind of time series, the black again is observations, all of the other colors are different model results. And you can see, there's some, occasionally a model will capture this, sometimes it won't. The validation suite was expanded. So now there's 5 metrics looking at a lot of different things. There's prediction efficiency and log spectral distance still. They added the root mean squared error to give you a specific measure of the accuracy of prediction, because the skill still doesn't tell you how much you missed by. It tells you how much better you are than another model. But then you're like, okay, so do I miss by 10 nanotesla, 100 nanotesla? The skill won't tell you that, but the accuracy will. Then there was a utility metric that was added to look at the potential value to a customer. If you're interested, it's actually kind of cool. Go look at this paper, work back through. I also like the related cost loss analysis in Matt Owen's solar wind prediction paper. And then there was the ratio of maximum amplitudes. And this is actually kind of a precursor for what was used for that transition, because in a lot of cases, the power industry say, look, we really care about the worst it's going to be in this interval. And so you want to know, what was the peak geoelectric field or the peak magnetic perturbation in that interval? And so if you can capture the peak, then maybe the rest doesn't matter as much. And so this is to get to that. The short takeaway is that the model's best in one or two metrics may not be best for what you're trying to do. You need to look at multiple things. So for example, the empirical models that were tested here had the lowest root mean squared errors and consequently the highest prediction efficiencies. The physics-based models had tended to have a better log spectral distance. So the physics-based models were capturing that power spectrum, the frequency content better. And part of this could be that the empirical models, they have to be fit. Maybe they were fit to minimize RMSE. Maybe they weren't intended to capture the frequency spectrum, where maybe they could have been designed to do that. And so here, actually, I think the physics-based models, again, are not performing as well in terms of error, but maybe more useful for the intended purpose of predicting GMDs, as counterintuitive as that sounds. If you think about the end point of application for, say, a utility, like that's where it's going to be more useful. And so here's the big one that folks probably know, is the community-wide validation of geospace model predictions. to support transition to operations. And so this was follow-on work that built on that GEM challenge. And it was this kind of community example of VVNA that I was holding up. So still uses horizontal geomagnetic field, but it actually just focused on the derivative of that, so the dBdt. And I pulled out a quote here, based on the earlier GEM challenge experiences and operational needs. So it's like, it's not just what do we want to show, but what do other people need to see? They decided to do this using event-based analyses. So this is the classification problem. And just to kind of illustrate how they are doing this, you take a time series. These are just red noise that I put together. You break this up into 20-minute non-overlapping windows. That's the vertical bars. And then in the bottom plot, you can see there's these red X's that have appeared. And those are the window maxima, which I've just put in the middle of each bin. And so these are then your quantity of interest, and you have to pick an event threshold in order to turn these into a yes, no, did I identify an event? And so let's put a threshold here at 10.5 because that splits it nicely. You can see the events are the ones above the line, the non-events are below the line. Now that we have events and non-events, we compare them and we dump all that into a contingency table. And in this work, they actually did this for 4 different thresholds so that you can see how well it performs at different levels of activity or different extremes of event. They used 3 validation metrics. I mentioned why at least 3 are usually used. And so there's the probability of detection, probability of false detection, and the Heidke skill score. And the results were aggregated across 2. So they were subsetted into high latitude and mid latitude because they can have quite different responses. And then they were aggregated to give you kind of a better certainty on the metrics that you calculate. We know the outcome. I'm not going to dwell on that. I am going to use my remaining time to talk about what's been going on since then and why is this still important. So this was a community-driven effort from the GEM challenge to the post-GEM challenge community validation. And that community work is still going on. There's the COSPAR International Space Weather Action Teams, which are more application or target area focused. And out of one of the early meetings of that, there were a set of community consensus papers on how to do validation for different topic areas. You know, if you want to do geomagnetic index prediction or a satellite charging environment, there are papers for those. If you're interested in the ionosphere, papers for those. And there's one on GMD prediction, which was led by Dan Welling. So there were 5 key community recommendations. There are a lot of authors on these. So it really was intended to be consensus. And that's almost like an informal kind of accreditation level. And so, you know, more data, if you have more data, then you can do a better job validating. Add more to your test set so you can better hit the range of conditions, include the effects of preconditioning. This one is saying, okay, we were subsetting previously by latitude bin, but you know, as Chigo was saying, there's differences between some night side phenomena, some day side phenomena. You may want to be able to understand how does this break down by local time, because this ties it back to phenomenology as well as pushing things forward to say, you know, how does this affect people who care about it? And so this is the skill score shown in that format from some graduate work that Sophie Graf has been doing in Michigan. And you can see actually, you know, the skill does vary by local time. Wow. And so there's a lot you can learn from this. Like, what is your model doing well? There's other ways you can subset it. You can, and they recommended subsetting by phenomenological grouping. So how well does the model do during sudden commencements, for example? And that lets you identify where the gaps are in your modeling. What's your model not doing well? And can you track improvements in that with time? And then they also recommended adding the frequency bias. And I note that adding that to the suite of metrics gives you the BHF triplet that I pulled out from the weather literature, plus the Heidke skill score. And so there's a really useful set of metrics. And again, frequency bias in that same binning. And you can see now actually, well, here we're seeing an over prediction for this lower threshold on the night side. We're predicting too many threshold crossings. The day side nailed it. So that's probably means that we're doing really well with the sudden commencements, for example. And this was an informal recommendation, so I'm listing it as 6 of 5. It's not enumerated in the conclusions, but they did say, as GIC forecasting evolves, further thought will be required concerning the value being compared to observations. And this is the quantity of interest. This is all being done with a time series of dBdt. And I can tell you that the time series of dBdt, and you may have gleaned it from looking at Chigo's slides, it's loosely visually correlated with the GIC, and it's loosely visually correlated with the geoelectric field. But, you know, one of the reasons that the models have a lot of trouble predicting the time series is because actually, you know, they're not a one-to-one very well correlated. However, the 20-minute maxima of dBdt and the 20-minute maxima of geoelectric field are extremely well correlated. And so that's why it's a great validation metric here, but maybe we actually do want to go to some better proxy for geoelectric field. Thank you. And so this has all just been 1D, you know, Chigo showed a figure very much like this, saying that actually localized enhancements are really important. This is from an EPRI report that I prepared, just showing one in Scandinavia. Just now, you know, they don't just occur over Canada. And there's, so these can happen on scales typically upwards of about 200 kilometers. They're rarely seen below that. And one approach you can take to try to characterize these is the regional to specific difference that was put forward in Andrew Dimmock's 2020 paper. And so this tells you essentially the difference between that featured station and the region average around it while excluding a station. And so it's useful for both science and as a proxy for something that is operationally relevant. Couple of things that if you're interested, you should go look at the follow-up paper by Dimmock et al., which was showing that as the grid resolution increased, the predictions converged towards the observed RSD. And then L. van der Griff over there is using global MHD to basically look at the RSD and say, why? And that's really exciting work. If you haven't seen it, go track them down. And you might be thinking, okay, well, I have a different problem. I'm not looking at the Earth. I'm looking at something 3D, 4D, 6D. Okay, great. You can aggregate and subset. We've talked about how that is happening in what we're doing. You know, I mean, you can't present things in 6D and have people easily understand it. You need to summarize, and that's what these are all about, is summaries in a way that is useful and understandable. There are statistical methods. If you've got too many dimensions, great. The distributions match. You can distill that down to a single number, or you can dig through the literature and find very specific metrics like the fractions Breyer score. But bear in mind, you need people to understand what they're looking at. And then there's probabilistic predictions. The dad joke of the day is in the top right, but there's a few different ways you can do probabilistic predictions. You can do conditional probabilities of events, like, you know, so there's a 0.4 chance of having an M-class flare, you know, doesn't give you a PDF. Ensemble modeling, you can combine those with ensemble dressing to get a PDF. You can directly predict a distribution, like using something like a Gaussian process regression. And so this image in the bottom is a probabilistic KP prediction by Shibaji Chakraborty, which used a deep Gaussian process. So that's kind of a machine learning augmented version of that. And what do we learn from this? In my remaining minute, I'm well aware, thank you. And so You can, for example, take your probability distribution and say, okay, now what's the probability that I exceeded this threshold? So you could have your, and I think this box shifted a point over, but still, you can say I had a miss in my model. There was an event in my prediction and I missed. But if you look at this probability distribution, you can say, well, actually, my model did predict a 40% chance of an event. So you didn't call it an event, but you had that information in there. There's a lot of ways that you can validate this. I'm not going to go through them. You can look directly, you can simplify things. You can look directly at the probability distribution functions. There are methods for all of these. And there's also visual approaches, which are really helpful for this, like the reliability diagram shown here, that a validation of the Met Office's space weather predictions. And the last thing that you can get out of this is understanding for why you missed. And so this particular example is driving a bunch of simulations to capture the uncertainty in the driver, in the solar wind driver. And where you're outside of that, significantly outside of that confidence interval, you know that it's not due to uncertainty in your driving. There's something missing in your model. So what are you not capturing correctly? And so this is a good feedback process. So there's some conclusions here. And in a second, I'm going to leave these up. I'm going to let, Adam push me off the podium. And then in a second, I'm going to flick to the next slide, which has some QR codes for additional resources. Thank you.
Okay, it's on, yeah. All right, I'm Jimmy Rader here from the University of Hampshire. I didn't see your first version of the talk, but it was very nice.
It was about the ring code.
It was
You
probably
wouldn't have
worth
liked
doing
it.
that, yeah. But what I would like to point out, it hasn't never really mentioned yet in our field is you looked at tornadoes, where lives are at stake. There's another field where validation is extremely important and where lives are at stake and where billions of dollars are at stake, and that's drug development. And one of the fundamental paradigms in testing drugs is blind, double blind, triple blind. In other words, the ones who actually run the metrics are not the ones who actually do the testing, or triple blind. They don't even pick the patients, so and we haven't been doing this so far, and one has to be worried about biases, because I think we would be naive if we would say there's nothing at stake. There's certainly a reputation at stake. There's a topic of possibly money at stake, a lot of money, when it comes to funding, so and one bias that is really, really obvious, and I wasn't aware of that, is that people still beat on the same storms. Who picks the storms? If you would take these Halloween storm or the other storms to run your metrics, a lot of models have already been sort of tuned to that, so I think at least at that point, the event should be selected by someone completely different, and the model should be run by someone who's not involved with the model, and the one who does the evaluation should not even know which model is what. So that's, I think, a real important thing to consider.
Yeah, no, I completely agree that that's an important point. Obviously, on that slide where I was introducing like the VB&A example, I went through those points, and that first section was, actually all of these groups, the developers, the data specialists, the people doing the validation, the stakeholders, they're all separate groups, and it could be better and it could be more like that more often, and that would be fantastic. The other thing, of course, as you mentioned, having for that testing, having completely unseen events. Now, there was some aspect of that in this exercise, but it wasn't complete. There's definitely value in having that kind of set of unseen events, but also you don't want to continually change that independent set, because if you're doing a validation against a different set of storms every time, for example, you can't trivially compare the results to previous efforts. And so you can't track the progress. So I do think there needs to be, essential and some unrelated work. There's a fantastic DOE report about hazard assessment for siting nuclear facilities where they're looking at, earthquake risks. And the way they do that is with, they have a huge database of events and probabilities, and everything is done with these distributions. And so it's a huge data set that is used consistently for every site everywhere. And the value in that is that, you can actually track that. So yeah, no, I absolutely agree. Just looking at, 4 storms, it's a useful indicator, but also they can bring in a lot of, can bring in bias.
Hi, Steve. Great tutorial. I enjoyed it very much. And do you want to guess what I'm going to comment about? As you know, I'm working on this imbalanced regressive methods, and this is also one metric that a lot of people don't know or don't care too much so far, but that's very important. Like, you show the tornado event, but in our community, the storms are even rare, more rare than the tornadoes, I guess. We need a metrics that will give us a more chance to, both predict the good storm events, but also maybe also predict the quiet time events. So we call it too often too quiet problem in the community. So I'm wondering, what do you plan to do about those, like too often too quiet problem or imbalance data set problem?
Yeah, I mean,
so metrics for that.
I mean, that's a good question. I mean, so yes, I mean, if you take kind of pretty much any scatter plot that's, plotting X versus Y in our community, you'll see like this huge density of points somewhere, and then a scattering of points elsewhere. And if you just do like a linear regression or some other, more complicated way of regressing that, you will generally, like, you will weight that density of points over the like the tails of the distribution. Generally, in some cases, the tails of the distribution, just because they're so far away, will actually dominate and pull your fit off from reality. And so you absolutely have to be careful about that. There are multiple ways of addressing that. The imbalance regression that you mentioned is one way to do that. But there are also differences in the metrics that you might use. And so if you look at the skill scores for a classification problem, for example, you would see, well, the ones that tend to get used, there's, the Heidke skill score and the Pierce skill score are probably the 2 most common ones. Now, what's the difference between them? The difference between them is how they're weighted. You could also look at the odds ratio skill score. The odds ratio skill score is strongly biased to positive predictions. And if you have an imbalanced case where most of the time things are negative, the odds ratio skill score is going to be favorable maybe to the cases that you're most interested in. Whereas the Pierce skill score is what they call equitable, which means that it actually weights each category similarly. And so there you may run into problems if you're looking at rare events. And so absolutely, this is a case where definitely, you want to actually dig in and understand what exactly is my metric showing me. And so, yeah, fantastic point. Thank you.
Thank you so much.
Okay, perfect.
Okay, so now I'd like to invite our student representatives to give some awards. Oh, we lost them.
We have to. Yeah, it's online. Okay, I'm going to start us off. Thank you everybody for participating in GEM this week. Especially thank you to our student moderators, volunteers. Everyone on this slide helped us in some way or another with moderating and just making things run more smoothly. We want to thank our student advisory committee, especially. They're always like stepping up to help. And we also want to thank especially Donglai Ma and Riley Troyer for doing student posters this year, tutorial posters that were hung up in the student hall this whole week. We want to thank them for starting that off. We're hoping that's going to be a yearly occurrence. So we want to also go over the winners of the poster competition now. So thank you for joining us here. We had multiple ties, so it's going to be a lot of y'all. We'll just do this. Okay, so because we had ties in multiple categories. Yeah, hold on. You're gonna sort them. Okay. Well, that one has a tie. This one? Oh, no, it doesn't. Okay. Okay, so for the best poster in the magnetosphere ionosphere coupling session, we've got Alex Schaefer. If he's here, please come up. If not, oops, sorry. Nope. Okay. In the category of the magnetotail and plasma sheet, we have two winners, Sanjay Chapuri and Tyler Mativier. Please come up. Come on up, guys. And then stay with us here because we're going to do a picture at the end. Congrats. Okay, in the category of general posters, we've got Alex Hoffman. Is he here? Not here. Okay, in the category of global system modeling, we've got Austin Smith. In the category of solar wind magnetosphere interaction, we've got two winners, Mike Coughlin and Chris Pritchard. And then in the category of the intermagnetospheres, we've got Sheng Huang. Okay, is Umbe here? She said she wanted a picture of all of us, but okay, Chris can get it. So everyone pose with your certificates. We need to get this on. Awesome. Thank you guys again. Congratulations. Okay, I'm going to give just a couple of closing remarks before we announce our student rep. I just wanted to thank everyone who has made my time as student representative possible. I especially want to thank Mei Yun Lin, who served with me last year as student representative. And also, of course, Shinju Chen has been fantastic as well. I've enjoyed working with both of them. It's been very different working with both of them, and I've liked each one for different reasons. I just want to thank everyone for a successful week. Thanks to our poster judges, those of you who submitted your poster judgings on time. Thank you especially. And I want to also thank the steering committee and NSF for just making all this possible and just being there for whatever the students need. I really, really appreciate all the work that you guys do and all the funding that we get to do all these very cool events. So now we're going to announce the junior student rep for this year. We had two candidates, Espen Frederick and Austin Smith, and our junior rep for the next 2 years is going to be Austin Smith. So best of luck, Austin. And I hope you enjoyed as much as I did. So thank you, everyone.
Okay, while Jing brings up my slides, I'd like to first welcome the focus group leaders for our last concurrent session today to come up and say just a couple of words to introduce their sessions, if they would like.
Hello, everyone. After the break in room A, we will have a session for CGS, in which we'll talk about the resources at the CGS, NASA Drive Center for Geospace storms. There will also be dedicated discussion on 2 resident storm events, November 2021 and March 2023. And you're welcome to join us. Thank you.
Peter is not here. Is there anybody online that wanted to speak to the sessions? Okay, well, in the interest of trying to get us out to the coffee break, I appreciate you sticking around. I have just a number of last words. So we had a wonderful GEM participation this year. We had 426 people in person, in total, sorry, 328 in person and 98 online. So we still had a very hybrid meeting. We had 149 students, 129 of those in person and 20 students online as well. 206 posters, and we had 8 family care recipients. You might have heard the children running around in the hallway, and I think that was a wonderful thing to have at the meeting. We had 149 underrepresented in STEM participants this year as well. There we go. So I want to briefly touch on anti-harassment and GEM climate. So I ask everyone here to please ensure you know how to access the GEM anti-harassment policy. We mentioned it at the start of the week, but I'll mention it again. We have posters in the hall, and I'd ask everybody to scan the GEM anti-harassment policy so you know where it is. So if anyone comes to you, or if you would like to come forward yourself, you may do so and submit a report to us. We take this very seriously. In addition, we have the GEM climate survey that Brian mentioned earlier in the week. So on Tuesday, please look out for that. And I encourage everybody to please participate. So there you can give us more general comments and feedback. Big thank you to the team at UNH and to Umbe, so Katie, Greta, Chris, Jing, and Umbe for all of the work they did putting together the website, the GEM app, and organizing the meeting and all the activities. So thank you very much. In addition, just like our student reps, we'd like to thank our NSF program directors and the NSF, Jalin and Lisa, for kindly funding the program and supporting us going forward. I'd like to thank again our student reps, Al and Sinju, for their amazing work. It's like organizing a second meeting that they do nearly entirely themselves. So thank you again. I want to thank Hyunju and welcome Fraz as the new leader of the GEMI program. It was a success this year as far as my participation went as a mentor again. And I hope that we can continue this going forward. I encourage everybody to sign up next year if you would like to be a mentee or a mentor. I wanted to thank the GEM steering committee for all of their work, organizing several of the sessions at lunchtime and other activities throughout the meeting. And finally, I want to once again thank all of you. So GEM would not be a success without all of your participation. So thank you so much. So just a reminder, we have some GEM focus group calls coming out soon, hopefully this summer. We're yet to decide. This afternoon, hopefully we'll come to a decision there and we'll let you know as soon as possible. We have 2 focus groups rotating off, so we will have room for more. We also have 2 at-large member positions and 3 research area coordinator positions that are open, and the deadline there is July 31. So I hope those of you that were interested had a chance to talk to us. You still can, we're still around. So if you're interested, please come and say hello. And to those that are rotating off, I thank you once more for your service. You all did a phenomenal job, so thank you. All right, so what's next? The GEM leadership talked with the CEDAR steering committee. So Mark Conde, the chair-elect, reached out to us, and we've started planning for a joint meeting in 2025. As you may be aware, we have some challenges now in June and July with new holidays, with other meetings that we wanted to attend. So our plan is to work the details out through community feedback. So please look out for surveys from both the GEM and CEDAR communities so we can come to a consensus as to the times and format that will work the best for everybody. We will need your feedback to make that decision. But I'm sure many of you are interested in next year. So we're going to Fort Collins, Colorado. It's about 1.5 hours north of Denver. And the dates will be July 23 to 28. And it'll be at the Hilton Fort Collins. For those of you that like beer, there's 20 award-winning craft breweries in Fort Collins, and I discovered actually that I think they produce 70% of the craft beer in Colorado. So, but it's a beautiful place. It's a bike-friendly city and a very welcoming community. So we're very much looking forward to going there. So of course, let's go to the break now. Please participate in the sessions this afternoon. I'll see the steering committee members at our meeting at 12:30. But otherwise, thanks again and safe travels, everybody.